Duke University invites Professor Alexander Moore to join us at Global Asia Conversation with the Scholars. I am Yuan Chen, Environmental Humanities Fellow of the Global Asia Initiative and the Franklin Humanities Institute at Duke University. Dr. Moore is an award-winning climate and health scientist and historian. His projects span 4 continents. He combined natural, archeological, historical, and public health data to understand climate change and to engage the public in the quest for solutions. His articles and interviews have been featured in more than 150 print and online media, including the New York Times, The Guardian, and the Natural History magazine. Dr. Moore, your expertise as both a climate scientist and a climate historian allows you to use both the natural and human archives to study the historical climate and also to study how the human past has been affecting and affected by the environment. One method you have often employed in your work is the study of ice cores. Can you please first give the general audience who are not familiar with this methodology a brief overview? For example, where do you collect the ice cores? What kind of information is stored in the ice cores, and how do you use them to understand the past?
Sure. Ice cores can be collected from any place that has a glacier or an ice sheet. Places like this are becoming less and less common in the world due to climate change. So in fact, we're losing a record of climate change and pollution and other human activities captured in the time capsule that is the ice. We're losing that a record of climate change because of climate change, which is very disconcerting.
Exactly.
So the places we've collected, well, the University of Maine, the Climate Change Institute particularly, with which I'm affiliated, has collected ice cores go as far, from the 2 poles, from North Pole, South Pole, so Greenland and Antarctica, to places like the Himalayas, which is also known as the 3rd pole because of how much ice is in the Himalayas, the tallest mountains in the world. And also the South America and the Andes, Alaska, and Chinese glaciers as well. The ice core that I have worked with the most for the last decade, essentially, comes from the Western Alps of Europe, the 2nd highest mountain there, called Monte Rosa, and a site called Cologny at the foot of the highest, not tallest, building in Europe called Margherita Hut, or Rifugio Margherita in Italian, which was inaugurated at the beginning of the 20th century by the Italian Alpine Club. And it brought Queen Margaret of Italy all the way up 4,450 meters. And she's the same person who gave the name to the Pizza Margherita, which is why I call it the Pizza Hut. Right at the bottom of that hut, there is a saddle, just a ice formation where the glacier has the almost perfect conditions for creating a very good record where the layers are thin. So the team extracted an ice core that was 72 meters long in 2013 from the site. The ice was actually kept in refrigerated cargo, brought over to Maine, University of Maine, Orono, and there the Climate Change Institute was analyzed with the state-of-the-art lab called the Keck Laser Ice Facility, engineered by the Climate Change Institute for the first time and used for the first time in 2015. Well, we published our first results in 2015. And basically, this system allows us to peer into the ice, to get data from the ice at very, very thin layers. And this allows you to pinpoint historical, go down to historical resolution, to historical detail. Before, ice cores were melted entirely, and once they were retrieved, and you would get, one data point per year if you were lucky, maybe 10 if you were really lucky. But in with the laser system, not only do we preserve the ice, but we also can go down to the historical resolution, to the historical detail, and actually get 300 data points per year, which is almost a data point per day for the last 2,000 years. So matching the historical data with the pollution and climate data that comes from ice core is really very powerful. And we did it for the first time with a collaboration between the Climate Change Institute at the University of Maine and the Initiative for the Science of Human Past at Harvard University, which it's a multi school initiative started in 2007 by Michael McCormick. I was a graduate student at the time. And now it encompasses School of Medicine, School of Engineering, School of Business, School of Public Health. We have faculty from all over. If you watched Jurassic Park, you remember perhaps that at the beginning they find a mosquito in amber, right, in fossilized amber. And the gimmick here, the idea was that you drill into the amber and get the DNA out of the mosquito, and the mosquito fed on dinosaurs, so that DNA is kept there forever, and you could recreate the dinosaur from the DNA. Right? All right. Well, imagine that an ice core is an amber for the atmosphere of the past, and each layer that is in the ice core is one of those pieces of amber, and it captures everything that people put in the atmosphere. The pollution from mining, lead and silver and copper and iron, or even just the changes in the atmosphere that happen because of natural shifts in the environment, or pollen. Even we don't use lasers to analyze pollen, but it's trapped there. Tephra, that is volcanic ash. We can find the volcanic ash in the ice core and then match it chemically to unique volcanic eruptions.
Can you give us one specific example? And can you please also tell us how that particular volcanic eruption affected the global climate?
Sure. I think the most famous one from our work, is the 536 AD event, most likely from Iceland, which created a year without a summer by covering the globe in ash, an ash cloud that prevented the sunlight from penetrating through in the same intensity. And so it didn't warm the planet the same way that it usually does. This event was chronicled, discussed by a few sources, Cassiodorus being one of them, but not a lot of eyewitness testimonies, not as many as you would expect, at least due to the fact that of the survival of sources, really, that's all it is. But it was identified by scientists too, separately, with various ice core and other and tree ring studies, and nobody knew where the volcanic eruption happened. Really, we had ideas, but not really a solid clue. And that came when our ice core, which is the only ice core that goes about 72 meters deep from the Western Alps, ours being the Initiative for the Science of Human Past and the Climate Change Institute, University of Maine, and a joint project. That ice core gives us ultra high resolution data. It's the highest resolution climate record still, I think, in existence. And an undergraduate from Harvard University who joined our project in 2016 and double majored in history and earth sciences, wrote an article where he learned and then produced the evidence learned how to analyze and then produce the evidence to chemically identify the chemical signature of the ash that was trapped in the ice core corresponding to the period of 536 AD. His name is Matthew Luongo, his first author on the paper, in which I'm also co-author. And he was really instructed by our colleague at Climate Change Institute, Andrei Kurbatov. Professor Andrei Kurbatov was one of the leading volcanologists in the world. The two of them identified Iceland as the origin of the volcanic eruption. The effects of it in the historical sources are what you would expect. People describe it as a veil over the sky, the sun looking more like the moon, and not producing the heat that it normally produces, and resulting in failed harvests throughout the known world. The impact was enormous. Failed harvests meant famines everywhere for a eminently urban population, particularly in the Eastern Roman Empire, that went without bread, went without grain. The entire Roman system of the annona, so-called, that brought grain from all over the Mediterranean, from Egypt particularly, but also Sicily and Apulia, and Crete, and Anatolia, to the cities of the Eastern Roman Empire, particularly Constantinople, was disrupted because there was nothing to harvest. We think that now, analyzing, I was actually working on precisely that right before we spoke. We think that there are multiple eruptions. Other historians and scientists have actually particularly scientists have identified other eruptions in the record. You see this, you can see this in the ice core because the ice captures the temperature as well. The way it works is wherever you are in the world, there is a ratio of oxygen isotopes. There are oxygen atoms that are heavier slightly, and oxygen atoms that are lighter. The heavier ones tend to hang around warmer temperatures. So if you go to the Caribbean, you'll have the heavier oxygen dominating. And if you go to the North Pole, you'll have the lighter oxygen dominating. That ratio is a known natural fact. And that ratio is also captured in the ice core. So you can actually have, from that ratio of oxygens, you can figure out what the temperature was in the past. And we do see a drop at the time. But we see it also in tree rings. Trees grow more in the summer and spring when rain and heat allow them to expand, to have more nutrients. If there is no sun, that's not possible. And therefore, tree rings show a thinner growth layer for that period. So in addition to the historical sources, which again are not very eloquent, we only have a few passages, not that many, that describe it. We also have tree rings and ice core, etc. And we think there are multiple eruptions after that. That in fact, this was a period of eruptions, particularly 540, 542, perhaps, where not as big as 536, but similar events occurred and significantly lowered the temperature of at least the northern hemisphere, according to the records we have. What was the effect of this on the whole ecosystem is what I would like to know, because 536 comes about 6 years before the greatest pandemic of the ancient world. And it also ushers in a period of cold weather, a cold climate of several hundred years that Michael McCormick and others at Harvard have named the late antique Little Ice Age.
the case study you just described is of really large scale. It's not just impacting the Roman Empire. So it's very likely that, it could also have affected Asia, in China, in Japan, right? But
Yes,
unfortunately, in China at the time, it's a period of very scant textual sources.
I
So
know.
I wonder how much evidence we can find that in the Chinese sources or Japanese sources.
I know, and this is the frustration of the pre-modernists. Um, often when we talk about the science of the human past or archeoscience or whatever we want to call it, this merging of the humanities, social sciences, and natural sciences, we have skeptics who say, you are prioritizing the science, you're prioritizing the scientific evidence, you're giving it more weight than the historical sources. And in fact, that's not the case. We are going to the natural scientific data because we are frustrated by the lack of other data.
Yeah, especially
And
talking
yeah,
about the first millennium. Yeah.
yeah, for the first millennium, it's very, very, I can show you a graph of the geodatabase of historical reports of climate events, which is the largest such geodatabase, which was created over the last 9 years at Harvard under my direction, and funded by the Arcadia Fund of London. And for the last 1,000 years, you have a pretty good variability. You have pretty good distribution of sources. The first 1,000 years, if you get 20 reports per year, you're lucky. And we're talking all events all over Eurasia, as far as Iraq, as far east as Iraq, and as far west as Spain and Portugal. So it is frustrating. And there are events in the past that we want to talk about, and that we can't talk about because we don't know enough. We're not prioritizing the scientific data. We are using it to complement the historical analysis and see if we are right. We keep asking these questions and see if we're right. We know a whole lot more about the 536 event now than we used to. And we know a whole lot more about the Justinianic plague than we used to, thanks to not only climate data, but also, most importantly, biomolecular archaeology, which has sequenced the genome of the disease from multiple victims, mass graves, throughout Eurasia.
I was looking at, Chinese sources around year 1000 these days. Actually, there are quite a few records of, what you just described about the volcanic ashes, possible volcanic ashes, about dust covering the clouds, covering the sun. So yeah, I will send them to you to see if it's possible to have any, volcanic records of them.
Absolutely, I'd be delighted. I would like to work on, for example, the 1278 eruption, which is most likely in Southeast Asia and Mount Rinjani, which definitely must have affected Asia more than it affected Europe. And we know it affected Europe, but we don't have any sources that say, hey, the sky was cloudy for a year. And I have a strong feeling that in fact is somewhere in sources that are not in the 7 languages I read. So maybe there are in the languages you read, and that'd be awesome.
Yeah.
And around the year 1000, I'm sure there's a lot happening around the year 1000 that is so far not fully explained. It's definitely a year of change and expansion, of migration throughout the world. And usually when you have that, you have an environmental event pushing people around. The world, nature, the environment is a large system in which there are many variables. And when you affect such a variable as big as climate, all the other variables are also affected.
Right.
So if you drop the temperature by a degree or two on average, which means you have extremes of 10 degrees below average on certain days, what does that do to the ecosystem, to animals, to water where it flows, precipitation, rain, whether there is any rain or not, food availability. We know that the plague in 542 was really one of the, in the ancient world, and unprecedented by scale. We had the Antonine and Cyprian plagues about 300 to 400 years earlier. They did not have the extent, to our knowledge, that the Justinianic plague had, where we're talking about 60% death rates. In Constantinople, the sources say they stopped counting the dead. They stopped counting after a certain amount because it was just overwhelming. They put them in towers. They didn't know where to put the bodies anymore.
Right.
So what could cause how does climate affect pandemics? Yeah, right. That's the question that I tackle.
Climate change and pandemic, and you're putting them side by side. So as you mentioned, none of these issues are new to planetary or human histories. One case study you have published, for example, is the Spanish flu and the 6-year climate anomaly from 1914 to 1919. And that is when the global temperature experienced some unusual drop. So can you briefly introduce that case study and also tell us, how does the past experience inform us and warn us?
As an economic historian, environmental historian, we think about history as a system, where there are multiple variables at all times, and nothing is preordained, right? Everything is based on contingency, on the coming together of multiple variables, multiple actors, multiple things, the environment, but also people, and also microbes and animals and migrations, etc. And if we think of all these things into a system, into a sphere, right, where we live, our planet, this interaction of things is what we call history. It's what we study, and that system changes based on these interactions and the will of people. People are very, very they're becoming one of the most dominant variables in this system. As we look at the changes that humans have brought to the system, we see how they affect the entire system remarkably. Climate change is a very good example. By increasing greenhouse gases, we are warming the planet. As a result, the climate is changing for everybody. What does that do? It affects the entire system, all the variables, the migration of animals, the availability of water, the availability of food, and all of those have, butterfly effects of their own. And that is how we have to think about that's how we think about the environment. As economic historians, as environmental historians, we think about the entire system that we live in as such. In the case of the Spanish flu, a 5 to 6 year anomaly that brought enormous precipitation, rain, and cold air over Europe during the period of World War I changed the system, the environment, enough to affect vectors of disease and also the spread of the disease as a result. So vectors of disease, today we have Lyme disease, for example, in the northeastern United States and pretty much throughout the United States at this point. The warm temperatures make the carriers of that disease, ticks mostly, reproduce much faster, or reproduce much longer rather, throughout the year, and as a result the disease spreads. In the Spanish flu case, the migration of the vectors of the disease, in that case birds, particularly mallard ducks, was interrupted by this climate anomaly, and the ducks contaminated water, and other vectors, I'm sure, contaminated the water in which soldiers were fighting up to November of 1918, when the war was actually over. But if you see any photos from World War I, you'll see that soldiers are wading in water constantly. They're living in water, trenches, with water up to their necks. Sometimes the tunnels in which they had dug under the trenches would fill with torrential rain, and people would drown. They were exposed to the water through wounds constantly. Trench foot was obviously a very common disease, and the
disease.
temperature and climate affected also their immune system. We are actually, our immune system is depressed. It functions less efficiently when we're exposed to extreme weather, particularly cold weather, which this was the case. Cold snow actually reached as far as Tripoli in Turkey. That there, there are lots of movies and documentation of this, particularly for the Australian and New Zealand troops that were stationed there. So we changed. So how did we change the system? I'll tell you at the end. But the fact remains, there was a 6-year climate anomaly that brought a lot of rain and a lot of cold weather over Europe. This interrupted the migration of vectors of the disease. Birds, particularly mallard ducks, reach 65% infection rate right around October, due to the ducklings actually not being exposed to the virus before, so they all get it. And when these birds, they're waterfowls, they're water birds, so they contaminate the water in which they are, and that contamination lasts for 2 weeks. So the water was overflowing into rivers and trenches, and people were exposed to it. People with lower immune systems, with weaker immune systems. So that is really and nobody had ever figured out, where does the infection from the Spanish flu actually come from? Well, it comes from this. But the question in the end that all reporters always ask is, why was there a 6-year climate anomaly? I mean, why did the weather get rainy all of a sudden? Why did it get cold? It's definitely due to the fact that for the first time in Europe, in European history, we were bombing the fields of Europe constantly and creating artificially dust in the air, unlike it's ever happened, unless you have a Saharan dust event during particularly winters that were really, really harsh. And dust functions in the air like a little magnet. If you know that there's water vapor in the air, right? Because you see the clouds, that's water vapor. When you introduce dust in the air, dust particles function like magnets, and they collect the water vapor molecules together, and eventually that becomes rain. So we actually affected the level of rain that Europeans experienced during World War I, due to the what we were doing to the environment. And you can see in the article we showed, I think it's first figure, this enormous blob, a climate anomaly right on top of a low pressure system, right on top of Europe. So it was really a perfect storm of human interaction, human impact onto the system, onto the environment, and the system in which people live, which is society and European battlefields, combined with already other variables like vectors of the disease, the presence of Spanish flu or H1N1 in the system, and this combination, this shock to the system, caused the creation. So how does that inform your question? How does that inform us today? By creating shocks to an system that's in equilibrium, or more or less in equilibrium, where there are established migration patterns of birds, which all carry diseases. All birds carry some virus. They carry their own disease environment with them, right? So as do we. We carry our own microbiome, our own virome in our bodies. As we move around, we acquire it. I think everybody knows that now that we're in a pandemic, and 2 years and a half, almost 3 years into a pandemic. So if we shock that system, the patterns of migration, the patterns of movement of people and animals and therefore disease change remarkably. And new people who were not, or animals, or are exposed to those diseases. And therefore you create an outbreak of disease in populations that were not exposed to those diseases. This certainly is happening with Lyme disease, right? So ticks are expanding in areas beyond their normal range, and they're living on animals that previously were in much lower numbers, like deer. We removed the wolves. There are many more deer. We gave a lot of food to ticks. Ticks are now proliferating and exploding in the Northeast. And as a result, cases of Lyme disease are proliferating and exploding in the Northeast. You can say the same about dengue fever and Zika virus. Both are expanding because the temperature in as far north as Boston is much warmer during the year, and so those areas are now habitats for mosquitoes that previously could not live in the Mid-Atlantic and New England area, and therefore we have an increase in. And this happens south too. We can spray, or we can find solutions to these problems. Usually, the global south has bears the brunt of the effects of this. So the bottom line is, when we shock a system with regional, national, continent-wide, or global events that humans cause, the result is a butterfly effect that we don't necessarily know, that changes the equilibrium of things, of natural equilibrium of things, migrations, where people go, what food they eat, what water they drink. And that makes it more likely that disease will emerge, or that other problems emerge, such as famines or extreme weather events. That's what I study, right? The interaction between humans and the environment, and how the environment then gets back to humans.
Right. Yeah. So, you mentioned pollen, you mentioned volcanic ash, carbon dioxide, and other things that can be trapped in ice cores and be studied. So, and all of those things are either contributors to climate change or products of climate change.
Yep.
From what you have collected from the ice cores, from the time capsules of the past, how much of the current climate change is attributable to human footprint, and how much is attributable to factors not controlled by humans?
So what we are experiencing today is without a doubt man-made. If you look at any of the graphs, I make these graphs every day to the present. I mean, not only about the last 1,000 years, but also about the last 50 years, because that's what usually reporters and the public are interested in. And if you look at the trends, even in the remotest areas of the world, this morning I was talking to a reporter about the Adirondacks, which is a park and just north of New York, one of the most well-preserved ones. And they thought that climate change wasn't affecting the Adirondacks. Well, as it turns out, in the last 15 years, temperature's been skyrocketing there as well. The amount of change that we've seen in the last 20 years is so drastic that there is really no other explanation. We cannot find another explanation. Solar radiation has not increased at the same pace. In fact, by solar radiation, we would probably be in a colder period rather than a warmer period, if you look at the cycle.
Right.
Milankovitch cycles is what they're called. There are multiple cycles, but Milankovitch cycles is what they're usually referring to. Some people talk about the wobbling and tilting of the Earth. I get this question all the time. Again, there's no evidence that we are in a period in that cycle that would suggest that the temperature would be higher by as much as it is now. as humans, humans have essentially doubled the length of the summer in the Arctic in the last 20 years. The amount of change that the Arctic has experienced in the last 20 years is equal to the amount of change it experienced from the transition from the Ice Age into the Holocene. We are creating a new epoch, not an age, but an epoch, a geological age. Artificially, methane is one of the greatest offenders. The more the world warms, the more methane is released, especially from permafrost, particularly in northern Russia. And we're seeing methane being released all over, which is why so many countries now are starting to, or cities are starting to ban new gas installations. In my mind, and I think 98.9% of other scientists, that this is a period of man-made climate change. And this has really started in 1800. You can see it. I mean, in my records, at the beginning of the Industrial Revolution, people thought that a city was prosperous if its air was polluted. We started doing that in the 1800s. So it's, we certainly did it, perhaps not immediately with warming, but we changed the environment, changed the atmosphere since the 1800s. I'm sure there are some natural phenomena at play now, but they're masked by what we're doing. Nature rarely does, creates extreme events as what we have been experiencing.
When you're using scientific records that go all the way to the present, the historical period, the pre-modern period, functions as a baseline, right? So the baseline pollution, for example, compared to where we are now, which is 30 times worse than the worst pollution ever produced by the pre-modern period. And so, when people try to denigrate and criticize the pre-modern period as, the Dark Ages, there are in fact environmental records that show us that the pre-modern period was not as dark, especially under certain lenses, right? Certain aspects, like the environmental aspects, and of course there are other implications for health and for modern climate change. So I find that this combination not only illuminates the past better, but it also illuminates the present better, and it rehabilitates history that so far has been set aside due to unfair prejudice created by mass media or misunderstandings of past societies.
All right, Alex. So thank you so much for your time today. So this is Alex Moore, the climate scientist, environmental historian, educator, and communicator. Thank you so much, Alex.
Thank you. Take care, Yuan.